Yeah, good afternoon and welcome to the second audio lecture. And in this lecture we are going to discuss about the time domain approach. And so this is the first way of encoding using a convolutional encoder. So time domain approach. So time domain approach. So in this time domain approach we do perform convolution. That is the reason why it has been given the name convolutional encoder. So how to encode the message sequence using time domain approach? So what do we require so for this approach? Okay, so let us denote our message sequence as this is the message sequence as M0, M1, M2 and so on, M capital L minus 1. So here L is the number of bits in the message sequence. For rest of our examples of different approaches, we do consider this 1 by 2 k equal to 3 encoder. So this encoder is rate 1 by 2 and constraint length capital K equal to 3 convolutional encoder. For the rest of the examples we do consider this encoder structure only. Now the important thing in time domain approach is if you look at this structure, there are two outputs, output 1 and output 2, so corresponding to the two modulo 2 adders. So in time domain approach, the first thing we have to do is for the given convolutional encoder structure, find out the number of output bits. So in this case we are having two outputs, output 1 and output 2. For these two outputs, that means for the two modulo 2 adders, we need to find out the generator sequences. So this is the first thing what we have to do in time domain approach. So for the given convolutional encoder, so look at the number of modulo 2 adders, that means number of outputs. For those two outputs, find out the generator sequences. So how to find out this generator sequence? So the generator sequence are nothing but impulse responses simply. So in this case we are having n equal to 2, that means the number of outputs is equal to 2. For a given convolution encoder of rate k by n, suppose you have been given a convolution encoder of rate k by n, k input bits, n output bits. So we have to find out n number of generator sequences. So in this example we are having two outputs, we need to find out two generator sequences. So the generator sequence are nothing but the impulse responses. So the impulse responses of the two adders. So what do you mean by impulse response of the two adders? So let us go see this. Now if you look at the encoder structure, so the impulse response. So what do you mean by impulse response? So impulse response is the output sequence of an adder for the input sequence for the input sequence 1, 0, 0 and so on. So here in this example we are having two adders. So for the input sequence of 1, 0, 0, we need to find out the outputs, the two outputs, output 1 and output 2. So those two outputs are nothing but the impulse responses for those outputs. So So how to find out the impulse response? Now let us see the structure. So we have this structure now. So we are having two outputs. So I will write down, as I said, the input sequence we have to take as 1, 0, 0 and so on. So input, present state, next state, output 1, output 2. So let us see this. So the input sequence we have to take a 1, 0, 0 and so on. The first input bit is 1. So initially we will assume the state of the shift register as 0, 0. I am having two memory elements, so 2 zeros. Now the first adder output is, as you look at the diagram, it is nothing but the modulo 2 addition of the input, the memory elements content, first memory element content, similarly second memory element content. So XOR operation of 1 plus 0 plus 0. So the first output is 1. Similarly, if you look at the second output, so it is also 1. So what will be the next state? Next state means after 1 clock pulse, the input bit, whatever the input bit is present here at this point, so it will be shifted to the first memory element, and the content of the first memory element will be shifted to the second memory element. So after 1 clock pulse, when the initial state is in 0, 0 with input bit as 1, the next state will be 1, 0. So this is the next state. Now, so as we said, the input sequence has to be 1, 0, 0. The second bit is 0. Now the state is 1, 0. So now the first output is 1, second output is 0. So next state will be 0, 1. Now the present state is 0, 1, next bit it is 0. So now the first output will be 1, second output is also 1. So next state will be 0, 0. So we reach it to the initial state. So at this stage we will stop it here. So we have to consider the inputs till we reach to the initial state. So now look at the two outputs. What are the two outputs? So the first output is 1, 1, 1. The second output is 1, 0, 1. So these two are the impulse responses for the first adder and the second adder. So for the given encoder in time domain approach, what we need to do is find out the impulse responses for the two outputs. So those are nothing but what we call as generator sequences, and these are denoted by, so the generator sequence is denoted by the first generator sequence, it is G of 1, because this is corresponding to the first output. So G of 1 is equal to G naught of 1, G1 of 1, G2 of 1. So which is nothing but 1, 1, 1. So that is the first generator sequence. And coming to the second generator sequence, it is G of 2. Sorry. So G of 2 corresponding to second output. So it is G naught of 2, G1 of 2, G2 of 2. So which is 1, 0, 1. So given any convolutional encoder, first find out the generator sequences. So the generator sequence are nothing but the impulse response of the two outputs for the input sequence 1, 0, 0 and so on. So as explained above, you need to find out the generator sequences. And you look at carefully. Now look at the first adder. So now to the first adder you got three connections. This is the first connection, this is the second one, this is the third one. So hold on. Thickness I will increase. Okay, so now see this. So for the first adder, the input is directly connected, the first memory element is directly connected, second memory is also directly connected. So there are three connections here. So we can write down 1 comma 1 comma 1. And coming to second adder, the input is connected, the last memory element output is connected, and the output of the first memory element is not connected. So 1, 0 and 1. So by looking at the convolutional encoder structure also, we can directly write down the generator sequences. So it is easier. So if the connection is made to the adder, please write as 1. If the connection is not made to the adder, please write as 0. So in this way you can write down the generator sequences. So by looking straight away, so the first adder, the generator sequence is 1 comma 1 comma 1. To the second adder, the generator sequence is 1 comma 0 comma 1. So in order to perform encoding procedure in time domain approach, the first task is to find out the generator sequences. So now we got the two generator sequences, then we got the message sequence also. So given a message sequence, knowing the generator sequences, we can find out the output of the convolutional encoder. So let us see an example now. So for the same 1/2 convolutional encoder, so we will consider some message. By considering that message, we will see what is the output. Okay, so for the present convolutional encoder, so we got, right, hold on. So for the given convolutional encoder, rate is 1/2 and capital K is equal to 3. Okay, so capital K is equal to 3, and the two generator sequences, G of 1 is equal to G naught of 1, G1 of 1 and G2 of 1. See, this 1 at the superscript indicates the output, so which is 1 comma 1 comma 1. Similarly, the second generator sequence is for the second output, G naught of 2 comma G1 of 2 comma G2 of 2, so which is equal to 1 comma 0 comma 1. So now let us consider a message sequence. So already we said that the message sequence is denoted as M0 comma M1 comma M2 and so on, ML minus 1. So in time domain approach, the two outputs, let us call the first output as X of 1, second output as a X of 2. So X of 1 is the output of the first adder, X of 2 is the output of the second adder. So in general, X of I is given by let it not be X of I, so let me put in another manner. So we are having two outputs now, so I will straight away write down 1 and 2. So yeah, so the first output X of 1, and when we perform convolution, so the first generator sequence has 3 bits and you got the message sequence as L bits. Suppose the generator sequence is having M number of bits and the message is having L bits. So when you perform discrete time convolution on these two sequences, that means generator sequence with M bits and message sequence with L bits, the output sequence will be having L plus M minus 1 bits. So the suffix I denotes which bit, so it is a 0th bit, first bit or second bit or whatever bit number. So when you perform convolution, so in order to find out the first output, I need to perform convolution of the message sequence with the first generator sequence, that is Xi of 1 is equal to, so we need to perform the convolution, discrete time convolution. So discrete time convolution is given by sigma L equal to 0 to capital M, GL of 1 M I minus L, where I equal to 0, 1, 2 and so on. So now this is the first output. So I indicates the bit index. So similarly you can write on the second output also. So xi of 2 is equal to sigma L equal to 0 to capital M, GL of 2 M I minus L, where I is equal to 0, 1 and 2 and so on. So the outputs are found by doing convolution of the message sequence with the corresponding generator sequences. So this is how we find out the output. So and the final output, as we see at the convolutional encoder, at the output we have a switch or multiplexer which switches between the two outputs. So the final output is given by xi, which is x naught of 1, similarly x naught of 2. That means the first output bit from the first adder, the first output from the second adder. Similarly x1 of 1, x1 of 2, x2 of 1, x2 of 2 and so on. So as said earlier, that the output we have a multiplexer, it switches between the two outputs. So it takes one bit from the first output, one bit from the second output, again from the first output, again from the second output, again from the first output, again from the second output. So in this way the encoder produces the output. So you need to remember these two convolutional expressions to find out the output sequences. So now let us do this example in time domain approach for the encoder given earlier. So first note down the generator sequences. So the generator sequences are g of 1 is equal to, so g naught of 1 comma, sorry, normal bracket, g1 of 1 comma g2 of 1, which is equal to 1 comma 1 comma 1. And similarly second generator sequence g of 2, g naught of 2 comma g1 of 2 comma g2 of 2, which is equal to 1 comma 0 comma 1. Now let us consider a message vector or message sequence 1 0 0 1 1. So as I said, so m0 comma m1 and so on, so m2 m3 m4. So here in this case L equal to 5, so we are having 5 message bits, and the length of the two generator sequences are 3. So let us denote with small m equal to 3, here also m equal to 3. So the message sequence length is 5, whereas the generator sequence length is 3. So in the output sequence that is in the first output we will be having L plus m minus 1, that means 7 bits. Similarly in the second output we will be having 7 bits. So for the given message sequence the first output will be producing 7 bits, similarly second output will also be producing 7 bits. So you may be asking, at the input we are having only 5 bits and the two output bits are, and the two outputs are producing 7 bits each, so totally 14 bits. But the convolutional encoder is rate 1 by 2, that means for every one input bit we need to produce only 2 output bits. So for 5 message bits the output has to be only 10 bits, but in this case we are getting 14 bits. So the reason I will explain later. Let us see the encoding procedure. So we are having the equations. Xi of 1 is equal to sigma L equal to 0 to capital M, and capital G L of 1 M I minus L, whereas I equal to 0 comma 1 2 and so on. So now let's find out the output bits for the first adder. I'll start with I equal to 0. So x naught of 1, that means the first bit of output 1 is equal to sigma L equal to 0 M. So what is M here? We are having two memory elements. So capital M is the number of memory elements. So L equal to 0 to M. So first L starts with 0. So Z naught of 1 M. I value is 0. 0 minus L means 0 minus 0, 0 plus G1 of 1. Next I value is 0, L value is 1, minus 1. So because we don't have M minus 1 and so on, the remaining times are 0. So the first output bit from the first adder will consist of only Z naught of 1 into M naught. So as we don't have M minus 1, this term is not required. So the output is G naught of 1 is 1 and M naught is 1. So output is 1. So the first output bit from the first adder is 1. Similarly x1 of 1. So in this case I equal to 1 now. So again summation L equal to 0 to M. So Z naught of 1. Next I minus L. I value is 1, L value is 0. So M1 plus G1 of 1 M naught, because I value is 1, L value is 1, M naught, plus next term will be G2 of 1 M minus 1. We don't have M minus 1, so after this no terms are required. So there are two terms here. G naught of 1 is 1, M1 is 0, plus G1 of 1 is 1, M naught is 1. So 1 into 0 0, 1 into 1 1, 1 plus 0, it will be 1. Next the third bit x2 of 1 from the first output. So it will be G naught of 1 M2 plus G1 of 1 M1 plus G2 of 1 M naught. So after this I will get M minus 1, so I need not write that. So 1 into 0 plus 1 into 0 plus 1 into 1. So it will be 1 the output. Next similarly x3 of 1 will be G naught of 1 M3 plus G1 of 1 M2 plus G2 of 1 M1, because I am having summation up to L equal to M only, capital M equal to 2. So after this no terms. So 1 into, what is M3? M3 is 0, sorry, M3 equal to 1. So 1 into 1, 1 into 0, 1 into 0, which is equal to 1 again. So next x4 of 1, G naught of 1 M4, next G1 of 1 M3 plus G2 of 1 M2, which is equal to 1 into 1 plus 1 into 1 plus 1 into 0. So which is equal to 1 into 1 1, 1 into 1 1, 1 plus 1 0, 0 plus 0 0. So I will be getting as 0. Next x5 of 1. So this will be G naught of 1 of M5 plus G1 of 1 M4. That's it. And right. Next G1 of 2 of M3, which is equal to M5. Do we have M5 here? So we don't have M5. So we are having from m0 to m5, so this term is not there, so only two terms. So g1 of 1 into m4 is 1 plus 1 into m3 is also 1, so answer is 0. Next, x6 of 1, which is equal to g0 of 1 m6 plus g1 of 1 m5 plus g2 of 1 m4. I think we don't have m5 and m6 bits, so only one term, so which is 1 into 1, which is equal to 1. So we got the 7 bits from the first output. So 1 1 1 1 0 0 1. So from the first output, so x of 1, the output from the first adder is given by 1 1 1 1 0 0 1. So this is the output from the first adder. So in a similar manner we can find out the output from the second adder. So again we'll write down the message 1 0 0 1 1, and which is m0 m1 m2 m3 m4, the second generator sequence, which is g0 of 2, g1 of 2 and g2 of 2, which is 1 0 1. One second. Right. So we are having this. The second output equation is given by x I of 2 is equal to sigma L equal to 0 to m g L of 2 m I minus L for I equal to 0, 1, 2 and so on. Again, as we discussed, the message sequence has 5 bits and the generator sequence has 3 bits. The output sequence will be having 5 plus 3 minus 1, 7 bits. So let us find out the 7 bits. So let us start I equal to 0. So x naught of 2 is equal to g naught of 2 m, I value is 0, L value is 0, so m naught. So next term will be g1 of 2 m minus 1. So we don't have m minus 1, m minus 2, so only one term. So g naught of 2 is 1 multiplied by m naught 1, which is equal to 1. So similarly x1 of 2, that means the second bit of the second output. So g naught of 2 m1 plus g1 of 2 m naught. So after m naught m minus 1 we don't have the terms. So g naught of 2 1, m1 is 0 plus 0 into 1, which is 0. Next x2 of 2, which is equal to g naught of 2 m2 plus g1 of 2 m1 plus g2 of 2 m naught. So which is equal to 1 into 0 plus g1 of 2 is 0 into 0 plus 1 into 1. So answer will be 1. Next x3 of 2, z naught of 2 m3 plus g1 of 2 m2 plus g2 of 2 m1. That's it, 3 terms, because we don't have g3 of 2. And this will be g naught of 2 1 into m3, which is 1 plus 0 into m2, which is 0, plus 1 into m1, which is 0. So answer will be 1. Next, x4 of 2, z0 of 2, m4, plus z1 of 2, m3, plus z2 of 2, m2. So 1 into 1 plus 0 into 1 plus 1 into 0. So it will be 1 again. And next, x5 of 2 is equal to we don't have m5, so g0 of 2 into m5 plus z1 of 2 into m4 plus g2 of 2 into m3. So we don't have m5, this term will not be there. So g1 of 2 is 0, 0 into m4 is 1, plus 1 into m3 is also 1. So answer is 1. And last bit, x6 of 2 is equal to z0 of 2 m6 plus z1 of 2 m5 plus g2 of 2 m4. We don't have m5 and m6, so which is equal to g2 of 2 is 1, m4 is 1, so output is 1. So you got the output as 1 0 1 1 1 1 1. So the second output x of 2 is equal to 1 0 1 1 1 1 1. So 1 2 3 4 5 6 7 bits. Earlier we got the first output as x of 1 is equal to 1 1 1 1 0 sorry 1 1 1 0 0 1. So the multiplexer at the output switches between the first output and second output. So the final output x is given by the first bit from the first output is 1, the first bit from the second output is 1, so 1 1. Next, the first bit from the first output is 1, the second bit is 1, here the second bit is 0, so 1 0. Third bit is 1, here also third bit 1, so 1 1. So here fourth bit is 1, fourth bit is 1, so 1 1. So fifth bit is 0, here it is 1, so 0 1. Sixth bit is 0, here it is 1, 0 1. So last bit here 1, here also 1, so 1 1. So this is the output sequence for the given encoder. So for the message of 10011, this is the message sequence. The output sequence is this one: 11, 10, 11, 11, 01, 01, 11. So but the encoder is 1/2 rate, so rate is 1/2. For every one input bit it has to produce 2 output bits. So here I am having 5 message bits, but we are having totally 14 output bits. For every message bit there are 2 output bits. So this output corresponds to the first message bit, second message bit, third message bit, fourth message bit, fifth message bit. So message bits are 1 0 0 1 1. But what about these remaining 2 output sequences? So these 2 are produced for the message sequence 0, 0, because so in this time domain approach the encoder will be again set to the initial state. So in order to set the encoder to the initial state, so we require capital K minus 1 tail bits. So in this case we are having constraint length capital K is equal to 3. So constraint length K is equal to 3. So in order to again keep the encoder to the initial state. So what is the initial state? 0 0. So I am having two memory elements. So in order to make the encoder to go back to the initial state 0 0, so we require k-1 tail bits. K-1 tail bits. So those k-1 tail bits are nothing but, here k equal to 3, so k-1 is equal to 2. So 2 additional zeros are added to the message vector. What is the message vector? 1 0 0 1 1, 5 bits. So but in order to keep the encoder state to the initial state again, so we require k-1 tail bits. So capital K equal to 3, so in this case we require 2 tail bits. So those 2 tail bits are nothing but 0 zeros. So totally how many message bits now? 1 0 0 1 1 and 2 tail bits. So totally 7 bits. So because considering the tail bits also, our message sequence is having 7 bits. So totally 14 bits at the output. So that is the reason why we are having 14 output bits. So the first 5 bits are the actual message bits and the last k-1 are the tail bits. Okay, and these tail bits are necessary to make the encoder go back to the initial state. Okay, so given any encoder structure, first thing you have to do is write down the generator sequences. So then write down your message vector m0, m1, m2 and so on, ml-1. So then using the equations, so convolution equations, find the output sequences. So then write the final output sequence. By multiplexing the switch or by taking the bits from the 2 outputs or 3 outputs, how many depending upon the number of outputs. So in the previous example we are having 2 outputs, so the multiplexer switches between the first output and second output. So 1 bit from the first output, 1 bit from the second output. So in this manner we need to do the convolution coding in time domain approach. So given any convolution encoder, so first do these steps in order to find out the encoded sequence in the time domain approach. So hope you understood. So refer the textbook once for any doubts. Okay, thank you.